Okay, question 2. We've got quite a big molecule, 11 carbons, C11H14O, and you've got proton and carbon NMR to work with. The standout feature, I would say, in both of these spectra is what clearly looks like a group of aromatic nuclei. So in the proton NMR, when you get a bunch of peaks around here between about 6.5 and 8, you think that's likely to come from a benzene ring. And those are the hydrogens on board that ring. And the important thing is that there are only 3 of them. Okay, so the total area for that is 2 plus 1 is 3. That's very important because remember that there are 6 positions on the ring, so if there are only 3 hydrogens, it means there are 3 other groups attached to the ring. So we know that we're almost certainly looking for a benzene ring with 3 substituents on board. In the carbon spectrum, this region is the aromatic region, so those peaks correspond to carbons in the benzene ring. And again, the significant thing is that there are only 4 of them, so there must be 6 carbons altogether, but only 4 peaks, and that tells you that you've got some symmetry, so that you must have 2 pairs of equivalent carbons, and then 2 other ones to give you the 4 altogether. So we're looking for a somewhat symmetrical benzene ring with only 3 things attached to it. Now if we come to think what exactly is attached to it, if we look at these 2 peaks in the proton NMR, it's very reminiscent of what we saw in the last question, where remember we saw an ethyl group, CH2, CH3, gave a quartet and a triplet. And we've got the same pattern here. The interesting thing is though that the areas, instead of just being 2 and 3, are 4 and 6. And that of course could mean that we have 2 ethyl groups which are equivalent. And they could be equivalent because we know from the C13 that there's some symmetry in the molecule. So that strongly suggests that we've got a benzene ring with 2 ethyl groups attached to it. And if you look at the chemical shifts, you can see that fits, because this one is just HCr, which you would expect for the methyl group. It's not attached to anything interesting, but if it's an ethyl group, the CH2 is next to the benzene ring, and that has the right shift. Okay, so far we know we have a benzene ring and 2 CH2, CH3 groups. And we can look at what else there must be just by looking at the molecular formula at that point. So we know we've got 6 carbons in the ring, plus 4 there, so we've got 1 carbon left over. We know there are only 3 hydrogens on the ring, and then there are 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 hydrogens accounted for between those 2 things. So again, that just leaves 1, and it leaves the oxygen. So that immediately, just from looking at the molecular formula, says that looks like it could be an aldehyde group, and miraculously that fits with the proton NMR, because a peak between 9 and 10 fits with an aldehyde group. If it's directly attached to the ring, like this, then you can see the next door carbon would be this one that have no hydrogens, so that fits with it being a singlet. And you can also see the C13 also fits with having a carbonyl-carbon there. So we're almost there now. It's just a question of how these things are arranged on the ring. So if we think about the possibilities, if our aldehyde group is there, one possibility is that the 2 ethyl groups are here, because that gives you the necessary symmetry that says this one is equivalent to that one. Another possibility would be that they're here and here. Because again, you've got the symmetry down the middle like that, which means these 2 ethyl groups would be equivalent. Any other arrangement wouldn't work because the ethyl groups wouldn't be equivalent, and you would also have more than 4 peaks in the aromatic region here because the symmetry would be destroyed. So it's got to be one or other of these. The question is, can we tell which one? Well, yes we can, because you can see if it was this, each of these CHs on the ring would have no hydrogen on the next door carbon, right? So if this was one of our CHs, the next door carbons are this one and this one. They neither of them have hydrogens on board, so that would give a singlet, as would that CH and that CH. So we would just get singlets in the spectrum, but you can see we actually have coupled peaks, so that tells you it's this one. Okay, and that fits with these two hydrogens being equivalent to each other, and they'd be split by this CH here, so that would give a doublet, so that peak comes from these two, and then this peak is split by both of these two equivalent CHs, so that gives a triplet, which accounts for that. So that is your structure. So again, the important thing is get the structure right, make it absolutely clear which sets of hydrogens correspond to which peaks, and then explain all those things about the splittings and about the symmetry and about the areas and all of that kind of stuff to make sure you get the marks. But that's the structure you should end up with.